How do power stations provide electricity to thousands of houses around a city? They don't use giant batteries. They do that by spinning a giant turbine like this. And to spin such a turbine, some power stations use very hot steam that blows over the turbines and spins it. Or maybe we can use the energy of the falling water. Or another example could be we fit these inside giant windmills and let the wind do the work for us. Whichever way you choose, all we do is spin a giant turbine. But how does turning something create electricity? Well, the technology is based on electromagnetic induction, discovered by Michael Faraday more than 200 years ago. The basic idea is that if you take a wire and move it up or down inside a magnetic field, it induces an electric current. So all we have to do is attach a coil of wire to these giant turbines and place them inside a magnetic field. As the turbine rotates, the coil starts rotating and the wires start moving up and down inside the magnetic field. That produces the electric current. And this can now be used to light up things. These devices are called electric generators. They convert spinning or mechanical energy into electrical energy. So let's look at them in detail now. So let's start by figuring out in what direction a current gets induced or generated in this coil once it starts rotating. So let's say, in our example, the coil rotates clockwise, somewhat like this. Now, how do we figure out the direction of the induced current? Well, we have already learned something called the Fleming's right-hand generator rule, which says you stretch the fingers of your right hand like this, such that they are perpendicular to each other. Then the thumb represents the direction of the motion of the wire. That is the direction in which you're pushing the wire. The forefinger gives us the direction of the magnetic field. Then our middle finger will give us the direction of the current. So all we have to do is align our right hand to make sure the thumb and the forefinger point in the direction of the motion and the magnetic field. Then the middle finger will give us the direction of the current. So let's use our right hand rule on the pink wire that is going upwards, as you can see, and on the blue wire that is moving downwards. So it'll be a great idea if you can first see whether you can try it yourself. So go ahead and use your right hand and see if you can figure out the direction of the current in the pink and the blue wire. All right, if you've done it, let's first start with the pink wire. Because the pink wire is going up, the thumb should be pointing upwards. The magnetic field is to the right, so the forefinger should be pointing to the right. And so if we align our fingers that way, it will look like this. Since the middle finger is pointing inwards, this means the current in the pink wire must be inwards. Similarly, for the blue wire is moving downwards. So the thumb will be pointing down. The forefinger will still be pointing to the right. And so if we arrange our right hand over here, it will look like this. The middle finger is pointing out of the screen. That means the current in the blue wire will be coming out of the screen. So what we have seen is if a wire is moving upwards over here, then the current will be into the screen. And if the wire is moving downwards, then the current will be out of the screen. Remember this will be important. So now let's get rid of the hands and put arrow marks to indicate the current. And now we can guess what direction the current will be in the rest of the wires. Since the current has to flow from the pink to the blue, we can say that the current has to move here like this. And then the current has to move here this way. It goes out. It goes to that external circuit, maybe where there is a bulb. We'll look at that later. Then the current comes back like this and it flows in this way. And the current continues to flow like this as the coil keeps rotating, because you can see the pink wire is still going up and the blue wire is still going down until we come to this point. Because now the pink wire starts moving downwards and now the blue wire starts moving upwards. Can you see that? Again, if I go back and come back again, notice the pink wire is coming down and the blue wire is going up. This means Now the current in the pink wire should be out of the screen because we already saw using our right hand rule. When the wire is going down, the current must be out. And in the blue wire, which is going up, the current must now be inwards. In other words, the current will now change its direction. This is the important thing. So the current changes its direction and it continues to flow this way until again the pink wire comes on the left side. Because now again, the pink wire starts going up, the blue wire starts going down, and as a result, the current in the pink wire will be inwards, the current in the blue wire will now be outwards, the current will again reverse. So every time our coil is in this position, which is perpendicular to the magnetic field, we will see that the current direction will flip. And so if you look at the entire animation now, it looks somewhat like this. Every time the coil comes in this position, perpendicular to the magnetic field, the current direction keeps changing. Now, of course, in the animation, I'm pausing the animation when my coil is perpendicular to the magnetic field so that we can see the current flipping its direction. But of course, in reality, the coil will be pushed continuously. There will be no stopping. There will be no jerking motion like we are seeing over here. Now, the next question we might have is how do we connect this coil to an external circuit, like say to a bulb? Well, we could connect it directly, right? Well, let's see what happens if we connect the circuit directly. Current will flow, no problem. But as the coil starts rotating, notice the wires start twisting and tangling and turning and whatnot. So that's going to be a problem. So to avoid that, we will not connect the wires directly. Instead, we will use an arrangement involving brushes and slip rings. It looks somewhat like this. So basically we have two metallic rings, the pink one and a blue one. And what you may not make out from my diagram over here is that each ring is connected to one wire only. So the pink ring is only connected to the left wire, and the blue ring is only connected to the right wire. And these wires are connected to carbon brushes, which is also conducting, and they are just touching these rings so that there is a metallic contact, but they're not stuck to it. So right now, there is a contact, the circuit is complete, and as a result, the current comes out of the blue ring, as you can see, moves this way, and current flows into the pink ring and goes like this. And when the coil starts rotating, as you can see, the rings rotate along with the coil. But since the brushes are not stuck to the rings just slip through the brushes. That's why they're called as slip rings. As a result, the brushes will not rotate. That solves the problem of wires twisting and tangling. And all the while, an electric contact is maintained. Now, once our coil comes in this position, we have seen that the current reverses. So now, the current will flow out of the pink ring, goes like this, through the bulb, and now enters into the blue ring. So for every half a rotation, the current through the bulb also reverses. Let's say when the current is flowing this way, the bulb glows blue. And let's say when the current reverses and flows like this, the bulb will glow yellow. And so now if you look at the entire animation, it looks somewhat like this. And so we have successfully built our generator. And what's interesting to see is that the current from that generator is continuously changing its direction. Such a current is called alternating current, or AC. And this might sound a little weird, but it turns out that when you want to transmit electricity over a long distance, like from the power station to your houses, then alternating currents, or AC, have some great advantages over unidirectional currents, or DC. And it's for that reason the current that we get at our houses, the electricity that we get at our houses, are all AC. And these generators are called AC generators. Finally, what if we want to build a DC generator? where we don't want the current direction to change. We want it to remain the same throughout. Let's say in this direction. How do we do that? Well, to build that, first let's get rid of these rings. All right, now to make sure that the current direction remains the same, what we will need is that these brushes to continuously keep changing contacts between these wires for every half a rotation. Let's see why. So if I want the current to flow this way, right now in this position, I can connect this brush to this wire, so the pink side, so that the current flows like this and comes out. But as the coil rotates, notice once it comes to this position, we have seen that the current starts flipping, current reverses. And so now, to maintain the current in the same direction, we would now require this brush to come in contact with this wire. That is the blue side, right? And then again, once we come to this position, again it flips, the current flips, and again we would want now this brush to come in contact with this side. And so as a result, can you see that for every half a rotation, we would want the contacts to keep changing. But how do we make sure that happens automatically? We can do that by attaching split rings. Split rings, as the name suggests, is a ring that is split in between, giving two half rings with some gap in between. Now let's see how this arrangement automatically changes contact for every half a rotation. So right now, this brush is in contact with the pink side. But as the coil rotates and comes to this position, the current reverses, and now notice the brush is in contact with the blue side, making sure the current still flows in the same direction through the bulb. Again, as the coil comes to now this position, finishing another half a rotation, again notice it has changed contact. It is now in contact with the pink ring, connected to the pink side. And this way, we have now built our DC generator, where the current only flows in one direction through any external circuit. And this arrangement, which helps us automatically change contacts, we call them as commutators. So split rings act like commutators. So to summarize what we learned, if you take a coil and spin in a magnetic field, then due to electromagnetic induction, a current gets generated in that coil. Now the direction of the current depends on whether the wire is going up or whether it's going down. And as a result, for every half a rotation, we see that the direction of the current keeps changing. And so this generator is called an AC generator because it generates an alternating current, a current whose direction keeps continuously changing. On the other hand, if we use split rings, then it acts like a commutator. It keeps changing the contacts for every half a rotation and makes sure that the current does not change the direction in the external circuit. We call this a DC generator. And so this is how we can generate electricity just by rotating a coil in between a couple of magnets.